Welcome to a new episode of the ITU Journal webinar series, where you can find insights and forward-looking research on future and evolving technologies. The ITU Journal is an international journal providing complete coverage of all communications and networking paradigms, free of charge for both readers and authors. This publication considers yet-to-be-published papers addressing fundamental and applied research, building bridges between disciplines, connecting theory with application, and stimulating international dialogue. Its interdisciplinary approach reflects ITU's comprehensive field of interest and explores the convergence of ICT with other disciplines. We count on your support to make this webinar an interesting experience. Please submit your questions via the Q&A channel at the bottom of your screen. All questions from the audience will be taken during the Q&A session after the talk. The meeting is being recorded and the recording will be made available on the webinar website. Closed captioning is also available for this event. You can enable this by clicking on the closed caption icon at the bottom of your screen. We hope that you will enjoy the talk and we encourage you to stay connected until the end for the Wisdom Corner. I will now give the floor to our Master of Ceremonies.
Hello, and welcome to the webinar series with academics of the IT Journal on Future and Evolving Technologies. My name is Alessia Magliarditi from ITU, the International Telecommunication Union, the United Nations Specialized Agency for Information and Communication Technologies. It is my pleasure to open the webinar today with Professor Raouf Boutaba from the University of Waterloo, Canada. We count on your support to make this webinar an interesting experience. So please submit your questions via the Q&A channel. We will address them to our speaker during the Q&A session. And after the Q&A session, please stay online. I will moderate the Wisdom Corner, live lessons. Professor Boutaba agreed to a personal chat. So he will share with us some lessons learned over the years that might perhaps be useful for some of you. Very pleased to introduce now Professor Ian Akilditz, Editor-in-Chief of the ITU Journal and President and founder of Truva from the United States. Professor Akilditz is Ken Byers Chair Professor in Telecommunication Emeritus at the Georgia Institute of Technology. He has established many research centers worldwide, including in South Africa, in Spain, Saudi Arabia, and Finland. He's Editor-in-Chief Emeritus of Impact Factor journals, highly cited and at the top of the most prestigious international rankings. He's visiting distinguished professors in several universities around the world. His current research interests include 6G wireless systems, terahertz communication, metaverse, and communication in challenged environments. Professor Akilditz, the floor is yours for your opening remarks to introduce our speaker and to moderate the Q&A session.
Thanks a lot, Alessia. Good morning, good afternoon, good evening, good night from Atlanta to all around the world. I wish happy Eid Mubarak to all Muslim friends and their families worldwide, as it is Eid al-Adha week currently. I again welcome you all to our ITU Journal Future and Evolving Technologies webinar series. We started this webinar series in 2022. We had some of the best researchers, including academic and industry leaders, talking on very popular and diverse topics in our series the last couple of years. please go to our journal's website and watch the previous webinars. They're also available on the YouTube. Your feedback and suggestions will always greatly be appreciated. We have another excellent researcher and speaker today, Professor Rauf Boutaba from University of Waterloo. Before I present Rauf, I would like to briefly talk about our journal. The objective of our journal is to bring the academic and industrial worlds together in order to establish a strong bridge between academia and industry. The idea for our journal was initiated back in December 2019, and our first issue was published in December 2020. Alessia was the key person in developing this journal together with me and Dr. Reinhard Scholl. It is an open access journal, no fees for readers, no fees for authors. The papers go through a rigorous review process, and we try to cover all forefront and timely research activities in the academic industrial world. The journal is a product of a big team effort, and I would like to acknowledge them here. Sergio Ono-san, Bilal Jamusi, Alessia Magliarditi, Erika Campilongo, and both Marias and many others for their work, efforts, continued support, and dedication for the success of our journal. I encourage you all to submit your papers, and also if you have ideas for special issues on popular topics, please do not hesitate to contact us. Today, I have great pleasure to present you our speaker, Professor Rauf Boutaba. First of all, on behalf of our entire journal team, I personally thank Rauf for accepting our invitation and giving this webinar today. Rauf Boutaba received his master's and PhD from University of Marie Curie, Paris in 1990 and 1994. In the 90s, he joined University of Waterloo in Canada as an assistant professor. Rauf Boutaba is a university chair professor currently and the director of the David R. Cheriton School of Computer Science at the University of Waterloo. Before, he served as the Associate Dean Research between 2016 and 2019 and the Associate Dean Innovation and Partnership 2019-2020 on the Faculty of Mathematics. Rauf also held an Henry International Chair in Network Softwareization in France, 17 through 22. He also held several visiting professors in the past, positions in the past, including at the University of Toronto, Pohang University of Science and Technology, in short form POSTECH in South Korea, Sorbonne University, like Paris, and the École Nationale Supérieure de Télécommunications, Telecom, now it's called Paris Tech, the Université Henri Descartes, Paris University, France, and fellow University of Rio de Janeiro, Brazil, and University of Bordeaux, France. As you see, he loves to be traveling worldwide and enjoying different cultures. His research interests are in the areas of network and service management. He has published extensively in these areas and received several journal and conference best paper awards. He is the founding editor-in-chief of the IEEE Transactions on Network and Service Management between 2007 and 2010, and recently served as an editor-in-chief of the IEEE Journal of Selected Areas in Communication between 2018 and 2021. Rauf has been an editor and a member of editorial board and special issue guest editor of several leading journals in network and communications, including IEEE Transactions on Mobile Computing, IEEE Communication Service and Tutorials, Elsevier Computer Networks, where I was the editor-in-chief, and I'm really thankful to him for serving for the journal for many years. He chairs the steering committees of the flagship IEEE conferences in the areas of network and service management. Some of them are like IFIP, IEEE International Symposium on Integrated Network and Service Management, in short form IAM. That's one of the leading conferences in that field or sub-area. And then IEEE IFIP Network Operations and Management Symposium, which is also in short form known as NOMS, and IEEE IFIP and ACM International Conference on Network and Service Management, CNSM, and many, many other services. The list is really long to go through all of them here. Moreover, Rauf served in various capacities in the organizing and technical program committees of a number of conferences, including Infocom, networking, IAM, NOMS, etc. So again, the list is very long. He's an extremely active member of the IEEE Communication Society, in short from ComSoc, and he led many, many offices over the last 20, 30 years. Again, I don't need to go through all of them here. And he also received several awards and recognitions, including the Silver Core from IFIP, the Hal Sobol, and Salah Aidarus. They were good friends of mine. Also, Joe Lo Cicero. I just thought about Lo Cicero. He died really young, same as Salah. And so they're all gone now. Dan Stokesbury and Donald McClellan awards from the IEEE ComSoc, and McNaughton Gold Medal from the IEEE Canada. He's an IEEE Fellow and also Fellow of the Engineering Institute of Canada, the Canadian Academy of Engineering, and the Royal Society of Canada. And he produced many, I'm not exactly sure about the number, but I just guess it's over 60 PhD and master students. Some of them became very successful in their careers. Currently, he supervises 10 PhD and 8 master students. Based on Google Scholar, his H-index is 77, and total number of citations to his papers almost 40,000. Rauf contributed many pioneering papers on the topics of network communication protocols and network management solutions, in particular on network virtualization the last 10 years. His papers on network management became classics in his almost 30 years career. His contributions, 4G, 5G, and 6G systems are very highly recognized. In recent years, he obtained many excellent results regarding network virtualization, about which he will talk today. He continues to produce high-class and impactful papers. Before I close my presentation, on a personal note, Rauf and I go back almost 30 years. We met at many conferences and events. We always had great time together, as we are on the same wavelengths, personal and professionally. He is a great fun to have as a friend. I personally thank him for accepting our invitation, giving this seminar today, or webinar today. Again, welcome, Rauf, to our webinar series. Rauf.
Wow, thank you, Jan, very much for inviting me first, and for this extensive introduction. I'm impressed about the work behind the scenes just to put together all this summary. Thank you very much. I'm very pleased to be here and give this webinar. And I believe I should start sharing my screen, right?
Yes, please.
See it okay?
Yeah, perfect. Thank you.
All right. Yeah. So my talk, as Jan just mentioned, is about network virtualization, and I thought I reflect on the work I have done over the years, and share with you, how this started, how network virtualization movement started, where it is used in practice these days, and the prospects about the future of network virtualization. So that's pretty much, and along the way, during my presentation, I will briefly touch on some of the works that we have done in various aspects of network virtualization. But let me start by maybe defining what network virtualization is, and maybe the best way to do that is to use a well-known analogy, that of compute server virtualization. So, as shown here, a server hypervisor could be Xen or KVM or other virtualizes CPU, memory, and disk storage, giving the illusion of sole ownership and control over these resources to the application, even though the resources are actually shared among multiple virtual machines, as shown here. So just as virtual machines are used to run application on different operating systems over the same server hardware, virtual networks are used, as shown here, to deploy different network services and carry their workloads on the same physical network. Similarly, a network virtualization platform virtualizes the physical network elements, including network nodes and network such as switches and routers and communication links, And in the next slide, I will show you how node virtualization and link virtualization actually would work. So starting with node virtualization, and any virtualization for that matter, involves resource partitioning. And for node virtualization, the resources to be partitioned are shown here, or a few examples are shown here. For example, for switch and router resources could be the CPU used for packet processing, the memory used, for example, for routing tables or interfaces and physical ports, etc. And for optical resources could be cross connects, transponders, ROADMs, and others. And for wireless resources could be base station transceivers, radio resources, access points, and so on and so forth. Now, the partitioning consists in slicing the physical resources into multiple independent virtual resources, with each virtual resource mimicking the functionality and performance of the physical resources. And here, isolation between virtual resources is really critical because it prevents from performance and security interferences between multiple tenants sitting on the same physical substrate. And isolation, or the level of isolation, depends on the partitioning method that is used. For example, if you use hard partitioning by dedicating physical resources such as ports of a switch or a wavelength in an optical fiber, that provides high isolation. In turn, when you use soft partitioning techniques, such as rate limiting, for example, or CPU capping, it allows for better sharing of resources, but a lower level of isolation. So link virtualization, in turn, depends on what is considered a link. For example, if the link is the physical medium, such as an optical fiber or copper wire or radio spectrum, the link virtualization is similar to well-known multiplexing techniques. So techniques such as frequency division multiplexing, time division multiplexing, wavelength division multiplexings are widely used to multiplex distinct communication channels over the same physical medium. In this case, the physical medium is split into distinct channels or time slots, and the sender and the receiver are under the illusion that they own the entire physical medium. Now, when performing physical medium partitioning, one needs to consider physical layer constraints and physical impairments. And as an example of physical layer constraint is, for example, spectral contiguity in optical transport networks. Now, link virtualization can be also done by manipulating the actual data as opposed to partitioning the physical medium. It can be done by manipulating the data, say the packets, and that are carried over the physical medium. And this is referred to as data path virtualization. Now, data path virtualization is typically performed by the nodes connected to the links using various techniques to direct data along the virtual links or the data paths, so to speak. Such techniques or popular techniques include frame labeling and tagging, as well as tunneling. Now, link virtualization can be performed at different layers of the protocol stack, as you can imagine. As we mentioned earlier, at the physical layer shown here, you can use multiplexing techniques such as FDM and TDM. At the data link layer, you can use frame tagging, such as done in VLAN and VXLAN. Somewhere between the link layer and the network layer, using encapsulation techniques such as GRE or encryption such as in IPsec. And at the transport and the application layer, usually overlay networking is used, and examples of application overlays include Tor for anonymous routing or BitTorrent for file sharing. But you can also imagine, for example, application layer multicasting done at the application layer as an overlay as well. So now that we have seen what node virtualization is and network and link virtualization, here we can discuss how they can be combined actually to achieve network virtualization. And the simplest definition of network virtualization is to make the physical network appear as multiple logical networks. So, for example, we have a physical network here. Network virtualization abstracts the physical characteristics of the physical network so that it appears as multiple logical networks. And each of these logical networks is referred to as a virtual network. Now, a virtual network can be a subset of the underlying physical network nodes and links, a subset of the resources, for example, in terms of packet processing capacity or link bandwidth. A more complete definition is shown here. I'm going to just read it. Here we define network virtualization as a networking environment that allows multiple service providers to dynamically compose multiple heterogeneous virtual networks that coexist together in isolation from each other, and to deploy customized end-to-end services on the fly, as well as manage them on those virtual networks for the end users, by effectively sharing and utilizing the underlying network resources that are leased or potentially leased from multiple infrastructure providers. So it's a quite long definition, but it has the merit of being complete. And as a matter of fact, we were able to have this definition adopted by the IETF working group on network virtualization. So before jumping in the bandwagon of network virtualization, it is maybe important to discuss why it is actually useful. And the most well-known reason given by the proponent of network virtualization back in the late 90s is that the internet is ossified. But what do we say? Why do we say actually the internet is ossified? If we think about it, it can be we can see that the existing internet, as we know it, is doing more than it was supposed to. And we are forcing it, obviously, to stretch beyond its limit. And each time a new problem arises, we solve that problem with some makeshift solution instead of looking into the reason that caused the problem. And the best example of such a band-aid is overlay-based solution. I mentioned application layer multicasting as one example. So they are very effective. They're easy to deploy, but they're still superficial. In fact, it is now almost impossible to resolve the root causes without disrupting everything, even if we can find one such root problem, actually. So one answer to this is no surprise, and that was basically a big research topic in the mid to late 90s, is to basically we needed a new architecture for the internet. Now, the problem is with such a new architecture must be able to solve all the existing problems we know of, security, for example, better support for mobility, et cetera, et cetera. But such architecture should also be able to handle everything that might come up in the unforeseen future, like new applications that emerge that have requirements that architecture cannot really support. So since it's not possible to come up with or to predict the future first, it is also not feasible to come up with or to create a universal architecture or a one-size-fits-all type of architecture. So a better idea, and this is an approach that I personally subscribe to, is instead of creating a one-size-fits-all architecture, instead is to creating an all sizes fit into one architecture, an architecture that can accommodate all different sizes and something that is open, programmable, and hence expandable based on future requirements. And this is where network virtualization can help, as it allows basically to create multiple or to abstraction or multiple logical networks that coexist atop the same physical infrastructure. So this obviously will have an impact on the business model in networking and among other things. The traditional role of network provider is split into two: an infrastructure provider that owns the physical infrastructure and manages the physical infrastructure, and a service provider role that leases resources from the infrastructure provider and create virtual networks that are customized for different use cases. For example, you can think of a secure, more secure network, or a network that better support mobility, and so on and so on. These logical networks coexist, or virtual network will coexist on the same substrate network, hence better sharing of resources. So we have, because we have new players in this ecosystem, we need to define new relationships between them. So there are service level agreements, which we already know are contracts between end users and service providers, but we can also imagine NPA or network provision agreements between service providers and infrastructure providers, as well as service provider interconnection agreements between different service providers, or IP interconnection agreement between infrastructure providers to provide services end-to-end. Now, in this new model, you can also imagine other players such as brokers that play the role of mediators between others. So now that we have introduced network virtualization, let's discuss some of the key challenges underlying this concept and some of the work we have done to address these challenges. And I will particularly focus for the rest of my talk, given we have limited time, on one fundamental problem in network virtualization known as virtual network embedding. So virtual network embedding deals with how to map virtual networks onto the physical network, which involves the mapping of virtual nodes onto physical nodes and virtual links onto physical paths in the underlying infrastructure. So a physical network, as shown here, can be modeled as a graph of physical nodes and links. And each of the nodes have resource capacity in terms of, for example, packet processing capacity. And each link has also resource capacity, typically in terms of bandwidth. Now, a virtual network is a collection of virtual nodes, as shown here in red, and virtual links forming a virtual topology with associated requirement in terms of node capacity, virtual node capacity, and virtual link capacity. And a virtual nodes is mapped onto a physical node or hosted onto a physical node. And we can have multiple virtual nodes coexisting on the same physical node. And virtual links are actually mapped onto physical paths in the underlying infrastructure. And the same way, we can accommodate multiple virtual network requests on, say, on top of the same physical network. So that's the virtual network embedding that consists into mapping these virtual network requests onto a physical network. Now, how is this problem solved? So most commonly, the problem is modeled as an optimization problem using variants of linear programming, mapping decisions or representing decisions by variables, different physical constraints such as resource limitation, technological constraints are expressed using linear constraints, format using those variables. And an objective that is a function of the variables is optimized, minimized, or maximized. Okay, the objective can be one of several possible objectives, such as shown in green here on the slide. It can be, for example, to maximize the number of successfully embedded virtual network requests, or maximize the revenue by, for example, embedding the most profitable requests, or maximize the resource utilization, or minimize the scheduling delay, that is the time between the request arrives until it is embedded in the network, or minimizing, for example, energy cost by limiting the mapping to a subset of the physical nodes and links, and thereby turning off or putting to sleep others to save in terms of energy consumption. Now, we can have one of these objectives that we want to optimize, or a combination of these of objectives that need to be optimized dynamically and over time. And in doing so, a number of constraints need to be satisfied, such as capacity constraints, already mentioned, due to the limited resources in the physical network, or some other physical constraints, such as wavelength contiguity constraint in DWDM optical networks. And that require establishing paths with single continuous wavelengths. Now, the virtual network embedding problem is known or proven to be NP-hard. It can be reduced to the NP-hard multi-way separator problem. So it's not straightforward to always find a feasible solution, certainly not in polynomial time. And so optimization techniques are typically used or restricted to solving small instances of this problem, and for large problem instances, heuristic algorithms are commonly devised. So in this slide, I show a row taxonomy of virtual network embedding algorithms in the literature. We can broadly categorize VNE or virtual network embedding algorithm into centralized, where the embedding is performed using a global view or relying on a global view of the physical network, or decentralized, where the VM is divided into agents in the physical network, and each agents perform embedding of part of the VM based on their local view. And through multiple iteration converge to an embedding of the entire virtual network. Now, for centralized VNE algorithms, one approach is to simultaneously embed nodes and links. This is referred to as one-shot embedding, but it is very challenging. Embedding nodes and embedding links are be hard. Embedding both of them jointly is even harder. So an easy approach that was basically that received more attention in the literature is to do that in two stages, two successive and coordinated embedding of nodes and links. And typically, most existing algorithms, what they do is basically assume that the node embedding is already provided, or use a greedy approach to embed the virtual node onto physical nodes, and then after that use a link mapping approach. It could be a shortest path algorithm or k-shortest path algorithm or any variant in order to embed the links there. So the problem with this uncoordinated mapping is that is basically it reduces, by assuming or doing that in two stages, you basically reduce the solution space, and that basically result in suboptimal embedding in the best scenario. Now, another approach, and we were first to basically achieve some level of coordination between the node and link mapping stages, and I'm going to discuss that in the next slide. And we come up with a series of algorithms under the umbrella name Vineyard, and including Divine and Irvine and other algorithms. And here the idea is basically to by trying to achieve some level of coordination between the stages of node mapping and link mapping, we improve the solution space and the embedding at the end. So very briefly, the idea behind Vineyard, as mentioned, is to achieve some level of coordination between the node mapping and the link mapping phases. And the underlying idea is to extend, as shown here. So we have given a virtual network request here, and this is at the bottom here we have the physical network black. And we extend the physical network graph by introducing meta nodes for each virtual node in the virtual network request, and then select a subset of the physical nodes shown here to in the bottom picture here to connect those meta nodes to. And the selection of these physical nodes can be basically based on the location constraint, because typically you want to place a particular virtual node in some geographical area to serve a given user population. So that's basically becomes a location constraint that determines which physical nodes to connect these meta nodes to. Once this is done, Vineyard then treats each virtual link, each of the virtual link in the virtual network request, as a commodity consisting of a pair of meta nodes. And as a result, finding the optimal flow for the commodity is equivalent to mapping the virtual link in an optimal way. And then by introducing additional binary constraints that force one meta edge to be selected for each meta node, Vineyard can effectively select exactly one substrate node for each of the meta nodes corresponding to a particular virtual node. And this multi-commodity flow problem is then formulated as a mixed integer programming problem with binary constraints on the meta edges and linear constraints on the actual physical network. Finally, the integer constraints of the mixed integer program are relaxed to obtain a linear program using deterministic and randomized rounding techniques. And that's how we were able actually to achieve coordination and improve the solution space for virtual network embedding. Now, existing solution for virtual network embedding, including Vineyard itself, assume that the substrate network to be operational at all times. However, this is not true, as you can imagine, and several studies, and I show some of them in this slide here, have shown that substrate networks are actually error-prone. And according to failure studies on IP backbones and data center networks, more than half of the failures are single link failures, and node and multiple link failures are less frequent, but it's not a rare event. And so, as you can imagine, also reliability is a major concern for infrastructure and service providers alike, since service outages can incur a high penalty in terms of revenue and customer satisfaction, leading to customer churn eventually. For example, Business Wire, and I show here some references, reported that North American businesses incur a loss of about $700 billion per year due to network downtime. And Gartner reported that every hour of downtime typically costs an organization about $300,000. So it is therefore very important to take into consideration physical network failures during the virtual network embedding process. And that's basically what we did back in 2010. In order to protect the substrate network or the virtual networks from the substrate network failures, we introduced the concept of survivable virtual network embedding, or SVNE for short. And the idea is basically to achieve a virtual network embedding that can tolerate failures in the substrate network. And we also proposed the first solution to the SVNE problem. We considered a single link failure in that in this particular work, and so which means that our SVNE solution tolerates a single link failure in the substrate network or the physical network, which is the, as mentioned in the previous slide, the most common failure scenario in practice. So in our solution approach, what we do is we reserve a certain percentage of bandwidth on each substrate link for backup purposes. And then before any virtual network requests arrive, we proactively compute a set of possible backup detours for each substrate link using a path selection algorithm. And we use the k-shortest paths here. And then when a substrate link fails, we in a reactive manner, or a reactive backup detour optimization solution is then invoked to reroute the affected bandwidth along the candidate backup detours. So over the years, there has been many proposals to solve the SVNE problem, including many of them from my group, shown here in this slide. We proposed a solution for the SVNE problem considering single link failure, as well as multiple link failures. Solutions for the SVNE considering node failures, as well as both node and link failures. And we also proposed several solutions to the SVNE problem in a specific context that of elastic optical networks. So next, I'm going to present one example of such a solution. We named Simple to illustrate. So Simple stands for survivability in multipath link embedding. And the main context here is that we assume that traffic splitting is possible. And hence, because traffic splitting is possible, we use multipath routing. So what Simple does is it guarantees full bandwidth of a virtual link demand in case of a single link failure, which is, as I mentioned before, the most common failure scenario in practice. For the less frequent scenarios of multiple link failures, Simple provides higher salvaged bandwidth. And most importantly, Simple guarantee VN survivability to link failure using backup resources, basically by requiring much less backup bandwidth compared to existing approaches, including SVN. because typically when you reserve backup resources to protect primary paths, usually that results in waste and bandwidth wastage. So we want to minimize that bandwidth wastage. And to illustrate through an example, let me show you how it works. So here we use color coding for primary paths. We use the black color, and for backup paths that are reserved again to protect against failure are colored in red. And we use as a baseline a proactive approach for SVNE called the full backup scheme. So in this case, a virtual link with demand X, the primary path, is embedded onto two disjoint paths with sufficient bandwidth, a primary path, capacity X, and a backup path of capacity X. So here you can imagine if a physical link in this primary path fails, then the disjoint backup path can be used to carry the traffic. So in this case, the bandwidth requirement to guarantee protection against this failure is 2 times X, right? So Simple operates on the principle of splitting of virtual link demand across different disjoint substrate path. As I mentioned, we assume path splitting and use multipath routing. So in this first example, virtual link demand is split actually into 3 disjoint substrate paths. So here, and X divided by 2 bandwidth is actually allocated to each of them. So in this case, 2 paths are used as the primary, then hence colored in black, whereas the third path is used as a backup. Since these paths are disjoint, at most one of them can be affected by a single substrate link failure. Now, if a substrate link in one of the paths fails, the 2 unaffected paths will deliver the requested bandwidth that is capacity X, right? Now, so here you should note that only half of the requested bandwidth is allocated to the backup path, right? So which is X divided by 2 in the red path here. So which means 50% backup bandwidth is saved in contrast to the full backup scheme used as a baseline here. Now we can extend this idea to higher number of splits, say K. For example, in these 2 figures here, we present the virtual link embedding scenario for K equal 4 here and for K equal to 5. And as you can see, 65%, 67%, and 75% backup bandwidth is saved in these 2 cases respectively. So now obviously we cannot just keep splitting paths because there are other constraints such as the existing path diversity in the physical network, but also all the overhead involved in, for example, packet reordering due to the path splitting and multipath routing. So that's basically some of the early work that motivated research in the area of network virtualization, and a plethora of algorithms have been proposed out there to solve, as I mentioned, one of the fundamental problems that is of virtual network embedding, and I showed you some of these. Now let me switch to where network virtualization has found most of the adoption in practice, and that is in the context of data centers. And so network virtualization has been adopted in data centers to guarantee bandwidth for cloud applications. And in the next few slides, I will discuss VNE, the virtual network embedding, in the context of cloud data centers. So traditionally, cloud data centers such as Amazon EC2 offer guaranteed computing and storage resources, but they don't guarantee bandwidth requirements. And so that because of that, performance isolation between users is not guaranteed. So commonly they just provide you with virtual machines with no guarantee on the bandwidth between these virtual machines. So if you're running an application that involves multiple virtual machines that communicate with each other, the network can become a performance bottleneck, even if you are guaranteed enough memory and CPU and storage resources. And so if because these environments are multi-tenant environments, so if one tenant user or application starts overloading the network, this will affect everybody else, all other applications that coexist in the same data center. And so, to address this limitation, a number of proposals have advocated to offer both guaranteed computing resources plus guaranteed networking resources. And those resources are offered in the form of what we call virtual data centers. What is a VDC? We have here shown a couple of VDC in blue and green. So a VDC consists actually of virtual machines, but also virtual switches and virtual routers, all of them connected through virtual links with guaranteed bandwidth. So you see here we have multiple virtual data centers that needs to be actually that coexist atop the same physical data center. And to further motivate why it is important to guarantee bandwidth requirement between virtual machines, part of a given application or for a given tenant in the data center, I show here 3 examples of typical virtual data center applications that have different topologies and hence different network requirements. So the first one is multi-tiered topology, typical for web services, for example, with front-end servers for dispatching service requests, and back-end application servers and database servers. And the partition aggregate topology is typical for query processing type of applications, and bipartite topologies are typical for batch and parallel processing applications such as MapReduce workloads. So these applications may require bandwidth guarantees along the links connecting the virtual machines. For instance, a congested link between a map task and a reduce task in a MapReduce application can actually delay the completion of the entire MapReduce application. So the data center virtualization guarantees, as I mentioned, not only compute and storage resources, but also guarantees bandwidth network resources for such data center application, hence its importance. So this slide shows or lists various works that we have done in the area of VDC embedding, including works on VDC embedding optimizing various objectives, works on survivable virtual data center embedding that guarantee the availability of the virtual data center over time, and works on VDC embedding that minimize the carbon footprint. So in the next slide, as an example, I will show you one instance of this work we call Venice, developed for survivable virtual data center embedding. So VDCs or virtual data centers, as you can imagine, and I showed a few example application topologies, have heterogeneous availability requirement as well, where availability refers to the amount of time a service must be available. In the figure here shown on the slide, these are referred to as, just to illustrate, as a virtual data center with low availability requirement, virtual data center with high availability requirement, and virtual data center with medium availability requirement. In practice, actually, for availability, we measure availability in terms of number of nines. Say, for example, 99% of the time availability, or 99.99%, and so on and so forth. Now, physical resources such as server machines, like the physical data center, or the physical switches, have also heterogeneous availability characteristics. So in the figure here, this is illustrated again here as an example as unreliable machines or reliable machines. So stated simply, the main idea behind Venice is to say, let's embed the VDC or the virtual data centers with low availability on the unreliable machines, and the high availability virtual data centers on the highly reliable machines, and say medium availability VDCs on a combination or a mixture of unreliable and reliable machines. So that's the intuitive idea. Now the question is how to compute the availability of a virtual data center or a VDC. Let's look at an example to illustrate the difficulty here. If we take again a three-tier web application shown here at the top in the figure, that is mapped on the physical data center, on physical servers in the data center, and this is shown by the dashed line here in the figure, showing each virtual, say, machine where it is mapped onto the physical infrastructure. We know how to compute the availability of physical machines, and this is known as the mean time between failures divided by the mean time between failures plus the mean time to repair. However, it is not straightforward to compute the VDC availability from that of the underlying physical machines where the VDC or the virtual data center is hosted. So here I show you how one can compute VDC availability, illustrated with, again, the previous example of a three-tier web application. The VDC web application consists of a single web server here, N1, and two application servers, N2 and N3, and two database servers, N4 and N5. The two application servers, N2 and N3, can provide backup for each other. So this is a replication group. And similarly, the two database servers also form a replication group. So the mapping of the VDC on the to the physical data center is shown in the bottom figure here. For example, the web server N2 and the application server N1 and the application server N2 are placed on the physical server N2 bar in the data center. Now, to compute the VDC availability, we can identify all possible failure scenarios, say SK, and compute the availability of the VDC using conditional probabilities. So to illustrate, again, we show three failure scenarios, F1, F2, and F3, each involving the failure of one of the three machines hosting the virtual data center or inside the physical data center. So in the first scenario, F1, at least one component in F1 becomes unavailable. So the scenario occurs with probability 1 minus the product of the availability of all servers and links in scenario F1. And in this scenario, the servers become unavailable with probability 1. So basically, the VDC availability in this scenario is 0 because servers become unavailable as the web server is not available. The machine hosting the web server fails or becomes unreachable because of a failure of a link or a switch in this scenario F1. Now, in scenario F2, case 2 here on the slide, all the components of F1 are assumed available, but at least one component in F2 in the physical infrastructure becomes unavailable. This occurs with probability P of F2 and shown here in the slide. And in this scenario, the service availability is determined by the availability of components in scenario F3. Now, in scenario F3, all components of F1 and F2 are available, and this occurs with probability P of F3, shown again here in the slide. And in this case, the service is available, and hence the availability of the VDC in this scenario F3 is equal to 1, as shown here. Now, using conditional probabilities, we can compute the VDC availability as the sum of the availability of the VDC in each scenario times the probability of occurrence of that scenario. And this is shown in the bottom of the slide here. So that's one way to do it eventually. But the problem is that even though this approach is of computing VDC availability is by breaking down failures into failure scenarios is intuitive, it cannot be directly applied in practice. And we actually show that computing VDC availability cannot be done in polynomial time, as we need to consider an exponential number of scenarios in the worst case. Basically, with n physical components on which the VDC are embedded, and each component can either be available or unavailable, there are of the order of 2 to the power of n possible scenarios to be considered in the worst case. Now, an interesting observation that I mentioned earlier is that it is unlikely to see a large number of simultaneous failures. And we have seen that most of the failures in production data centers are single link failures. And also, if we take, for example, 3 nodes, each with the availability more than 95%, the probability of seeing all 3 nodes fail simultaneously is at most, or is less than 0.00013. So it's quite small. So a fast heuristic can be devised that computes availability using scenario SK that involve at most 3 simultaneous failures. And this can provide us with a lower bound on VDC availability. And that's exactly what we do. And accordingly, we devise a greedy scheduling algorithm that for each received virtual data center request, do an initial embedding that embeds 1 node from each of the replication groups. And then in a repeat loop for each remaining component, compute a score that is the availability improvement minus the resource cost, and then embed the component with that, basically the highest score. And we do so until the VDC availability is achieved or all nodes are embedded, at which time we embed the remaining component greedily based solely on resource cost. So that's in a nutshell the idea behind Venice for survival virtual network embedding, virtual data center embedding. Now I'm moving to the third part in my talk here, focusing now on what is really happening in terms of the future prospects for virtual network network virtualization adoption in practice. So and this is a more recent incarnation of network virtualization in the context of 5G and beyond mobile communication network, though in the literature is mostly referred to as network slicing. So before that, let me take a quick look at 5G network and services. The 3GPP, actually the ITU standard, identified 3 major classes of services with different quality of service requirements, known as enhanced mobile broadband, which delivers gigabytes of bandwidth, massive machine type communication, promising to connect up to 1 million IoT devices per square kilometer, and ultra reliable low latency communication services that promises to offer 1 millisecond latency with high reliability. So it is obvious that it is difficult to satisfy these differing quality of service requirements of all these services on the same physical network, while not obviously increasing capital and operational expenditures substantially. And network slicing or network virtualization, if you will, is obviously the way to go because it allows the deployment of multiple logical networks as independent business operation on a common 5G network infrastructure. So this slide shows a 5G network architecture. The radio access part consists of hybrid radio access technologies, here legacy antennas and next generation antennas where the remote radio heads and the baseband units are separated, and the core network consists of multi-tiers of cloud data centers or data center networks, including edge, metro, and core clouds, and the radio access network and the core mobile networks are interconnected via transport network, and the transport nodes can be optical nodes or are commonly optical nodes interconnected via fiber optics. Now, as discussed in the previous slide, we have the 5G services, EMBB, mostly designed for applications such as augmented reality, ultra high definition video streaming, and others. Also, the ultra reliable and low latency communications for applications such as automated traffic control, connected vehicles, and remote surgery, and others. And massive machine type communications for IoT applications such as smart cities, smart agriculture, and many others. Now, 5G slicing enables these various classes of services to coexist atop the same physical infrastructure and share the physical network resources. In the case of 5G, for example, a slice consists of a set of network functions, as well as compute and storage and network resources. And depending on the service class, a slice can span from the radio access network to the core network, or can have all its network functions located at the network edge, for example, to achieve minimal latency. So the orange slice shown on the slide here represent a network slice for eMBB type service. Here, the network functions are typical functions in the 5G core, such as the access and mobility management function and the user data management function and others. We can imagine a blue slice here representing the ultra-reliable low latency service, and due to its delay-sensitive nature, all network functions are located at the network edge, as well as a green slice here representing massive machine type communication services. Here we see two types of network functions, one that aggregates traffic collected from IoT sensors at the edge, and another that splits the packets for processing at the core. Now, as seen in the previous overview of 5G networks and 5G and beyond, actually, networks data centers are everywhere inside the telco infrastructure, from the core to the edge and beyond. And the goal is to here in embracing cloud technologies is to benefit from from cloud computing features such as cost reduction through better resource sharing and economies of scale, as well as flexibility and elasticity in terms of scaling up and down resources on demand. So these data centers in the context of telco networks, such as 5G mobile networks, are used to host various network functions, including core network function, as well as functions providing value-added services, such as security services like firewalls, and performance services such as load balancers. And in these data centers, the network functions actually are virtualized and implemented as software appliances that run on top of commodity hardware, and they are commonly referred to as virtualized network functions, or VNF for short. Now, this slide shows or illustrates the disaggregation in 5G core and access networks, leveraging virtualized network functions. In the core, the evolved packet core functionality is decomposed into finer grained functions, including user plane functions and control plane functions, such as access and mobility management function and session management functions and others. And in the access network, or in the RAN or the traditional RAN functionality, such as radio link control, medium access control, and others, is disaggregated into radio units, distributed units, and centralized units, and deployed as virtualized network functions. And this allows for flexible functional split that can be tailored to support specific use cases. Now, a 5G slice consists of a chain of virtualized network functions hosted in the RU, DU, CU, and core, and virtualized links or virtual links connecting them. The VNFs of slices can be placed anywhere inside the network based on the VNF's delay requirement and resource availability at the different sites. For example, CUs have higher compute capacity but increased delays. And DUs, or the centralized units, have limited compute capacity in bandwidth, but lower delays because they typically sit at the edge of the network or placed at the edge of the network. Now, 5G slicing brings new challenges in order to do that in this context, and because there are more moving parts that we have seen. We have disaggregated and virtualized core and RAN, which add complexity, and also virtualization and disaggregation broadens the surface for faults and makes troubleshooting more complicated. So we have recently addressed various aspects of 5G slicing. As shown in this slide, we did work on joint slicing and admission control, slice KPI monitoring, fault detection and localization. And as I mentioned, this is more complicated in the context of 5G. So to tame the complexity of slicing in this context, we leveraged quite a bit AI and machine learning techniques in these works. Again, here to illustrate, I'm going to show you one sample work that we have done in the group the one that focuses on joint slicing and admission control. So as I mentioned, slicing pertains to placing these sets of virtualized network functions belonging to different slices in substrate networks such that latency and resource requirements of the functions are met. And now the problem is when there is a large number demand for slices, admission control becomes important and is commonly actually employed. Now, admission control can learn specific or slice requests arrival patterns and decide to admit or reject an incoming slice request based on its requirements and the revenue it offers. If we look at the literature, most of the works considered slicing and admission control independently. And this is actually a problem because when doing admission control and overlooking slicing, typically this is done by modeling the network as a single knapsack. As a result, the admission control decision can differ based on whether a constrained link would be used by a slice embedding down the road and leading to a bottleneck in the network. So, and that's why we argue that coordination between slicing and admission control is critical. And in order to do that, we jointly consider slicing and admission control with the objective of maximizing revenue for the infrastructure provider in a setting where there are different priority classes for slices, and the revenue depends obviously on the priority class. And to address this joint admission control and slicing, we formulated the problem as a Markov decision process, where the state includes information about the network and the incoming slice requests, and the required actions include admission decisions and the placement decisions for each slice component, while the reward for any actions is the cumulative revenue gained by accepting and successfully embedding slices in the substrate network. And we used a multi-agent deep reinforcement learning to learn the optimal policy for this Markov decision process. And we used actually two separate agents, one for slicing and one for admission control. And we designed these agents to cooperate with each other to accomplish joint slicing and admission control. Now, we chose to use separate agents because the separation, in this separation, each agent only needs to explore a smaller action space in comparison to the combined slicing and admission control action space. And that basically led to comparatively faster learning. Even with that, due to the large time interval between episodic rewards in the case of large network topology, the learning can still be very slow. And also, if the network topology changes, the learn policy become quickly unusable. So to address the issue of slow learning, we use reward shaping, and rather than using the gained revenue as a reward, we design a custom per step reward that leverages domain knowledge. For example, we account for the number of constraint violation and decrease the reward for each violated constraint. And in addition to that, we also customize each agent's reward such that it is maximized only when the agents cooperate together. So in our first work, we used a fully connected neural network or a multi-layer perceptrons. Although this approach was actually successful in addressing joint slicing and admission control in a small-sized static network, it could not cope with dynamic and large-scale network topology. So and changes actually in the network topology can occur for different reasons, including link node failure or network upgrade expansion. And in this case, training a deep neural network from scratch on each topological variation can be prohibitive, especially in a highly dynamic environment or under tight service and delay requirements. So therefore, in our more recent work, we used the graph attention networks, which is a form of a graph neural network, as you know, and this neural architecture is optimal for graph-based data and can also account for changes in the network topology. Now, let me finish here with a few takeaways, putting everything together. So clearly, network virtualization is already transforming the networking landscape, I believe. Many products are available out there for device virtualization, including virtualized switches, routers, and middle boxes, such as virtual firewalls and others. And the virtual router market alone is expected to grow to billions of dollars in the next few years. Now, It is also important to acknowledge, however, that this transformation is still in its early stages. While many products are available for device virtualization, the bulk of deployment has primarily occurred in cloud data center, as mentioned earlier. And unlike traditional telecom operators, cloud providers such as hyperscalers have the advantage of deploying infrastructure from scratch without the burden of legacy networks, which is the case for telco operators. So this clean slate allowed them to implement network virtualization solutions more readily and at scale. In the telco world, most significant network virtualization adoption is happening as part of the evolution of mobile communication networks, especially since the rollout of 5G networks, driven by the need for support to support use cases with stringent and differing performance and reliability requirements. And there is hence hope to see network virtualization deployed throughout all of the RAN, transport, and core networks. Another good thing happening is in the area of standardization within standard bodies like the ITU3GPP and ETSI, as well as industry alliances such as Open RAN Alliance, which are playing a pivotal role in paving the way for the adoption of network virtualization. Now, telco operators worldwide are conducting trials as we speak. So there is real hope there. But let me finish with maybe some of the challenges that are yet to be addressed in order to achieve what I call end-to-end network virtualization, because this unfortunately remains, or most deployment or most solutions out there remain constrained to a single technology or a single administrative domain, such as single mobile network operator. So end-to-end virtualization across multiple administrative domains remain unrealized in practice, and this can be attributed to multiple factors. Maybe the most important one is the existence of multiple stakeholders, and there are a number of issues that need to be addressed before end-to-end network virtualization becomes a reality, including interoperability issues, security concerns, regulatory complexity, even more complicated, and while end-to-end network virtualization deployment in practice may be limited at present, it definitely presents an invaluable opportunity as a test bed to experiment with new architectures and protocols. And this is exactly actually what we have done as part of the a project here in Canada we called Smart Application on Virtual Infrastructure, or SAVI project. And I'll just say a couple of words about this. Before concluding, so the SAVI, or Smart Application on Virtualized Infrastructure, is a pan-Canada testbed that leverages network virtualization end-to-end in edge data centers, core clouds, and transport networks to provide a platform for driving innovation and experimentation in network technologies and smart applications. The table in this slide here shows the SAVI infrastructure resources that are currently deployed in the 8 nodes, 7 edge data centers, and 1 core cloud across 7 Canadian universities from east coast to west coast. These are connected through the provincial and federal high-speed research networks, namely Orion and Canary. And SAVI is also federated with networks in the US, including Genie, Cloud Lab, and Chameleon. And we also deployed 1 SAVI node in South Korea, specifically at POSTECH. So this is happening worldwide as we speak. One recent example is a similar project called Slices that has been funded by the European Union, involving 15 EU countries with an investment of 137.7 million euros to provide a fully virtualized European-wide research infrastructure. And so such research platforms and recent trials by major industry players speak to the increased interest in the realization of network virtualization end-to-end, which I hope will happen sometime soon. And I believe I took a little bit too much time, Jan. So I finish here, and I thank everyone for listening to me.
Thanks a lot, Raouf, and excellent talk. Thank you. And everything is clear, and I hope there will be some questions from the audience. Please type your questions in the Q&A box so that I can read your questions to Raouf. And since I'm waiting for some more questions, I would like to ask you, as you know, this network slicing is well understood for 5G systems, and everything is in place so far. And like people are talking about self-organizing now, so zero-touch networks, not organizing networks, so they self-controlling networks, right? So in other words, automatically using these machine learning techniques, AI machine learning techniques, to do all this network management. The problem is that OPEX and CAPEX are very expensive in the current systems, also in the future systems. They are trying to create these automated networks. And so these AI and machine learning techniques will play a major role for that. So how do you think that your research, especially in this network slicing, be done automatically and either centralized way or distributed way?
Yeah, excellent question. I think this is definitely one of a big concern for network operators. You know, the capital and operational expenditures in particular, actually, which is the most significant part of the costs involved in running a network, and so there is this. Network automation in general has been the holy grail of, as you know, Jan, of network management research for decades. And actually, I did my PhD over 30 years ago in network automation. This has actually been had seen not so much deployment in practice, and there are many factors that we can to which this can be attributed. But most important is now the timing is really good for that, to close that control loop, Jan, including so networks can monitor themselves autonomously, collecting data, analyzing this data, leveraging machine learning techniques, supervised and unsupervised learning techniques, and then devising plans of actions to deal with changes in the network, or for example, anomalies that are detected in the network, and using techniques such as reinforcement learning and scheduling the optimal executions of those plans, closing the loop on the network. Again, here, reinforcement learning techniques can be very handy for scheduling plan executions. And then all the virtualization and the softwareization that allow network programmability allow you to easily effect those changes in the network. So I program the network so basically the combination of or the recent breakthroughs in AI and machine learning and the maturing technologies of network virtualization and network softwareization together, I think, make the long-time vision of network automation, minimizing human intervention in the control loop, I think feasible. Now, in terms of research, since you asked me the question, this is obviously my primary research of area, like network management and automated network management in particular, and closing the loop. So though I haven't really mentioned this during my talk today, I have actually major projects in this area, including actually the automation of slice orchestration in 5G and beyond networks, the entire life cycle of slices, from slice creation to resource provisioning for slices, resource scaling, or handling failures when they occur, or performance degradations in a sliced 5G network, and so that's basically a major project that has been ongoing for a couple of years here at Waterloo, in partnership with Rogers Communication. Rogers is the largest telecom provider here in Canada, and so part of this project, Rogers deployed a full-fledged 5G network on campus. So it is used for many research projects, including self-driving buses around campus and infrastructure inspections, including using drones and all kinds of sexy applications. My work is mostly under the hood, basically building the engine that will facilitate such applications, focusing on network automation in a fully sliced 5G network. And actually, as not on Friday last week, Rogers announced a chair in network automation that was generously assigned to me. So yeah, so I'm very active in this area. We develop all kinds of algorithms leveraging machine learning techniques, various machine learning techniques for fault management, performance management, slice orchestration, to name a few, as well as security.
Good. Congratulations for the chair. And so in other words, the message is that to achieve these self-controlling networks, right? So everything will be based on AI and machine learning techniques. So all the slicings, network virtualization research we have done so far, somehow they have to be rehashed and with AI machine learning techniques could be somehow upgraded to achieve those controlling networks. This self-organizing networks comes to my mind always. Controlling networks or zero-touch networks. So there are many more questions in the meantime. So it's good that we took the time. So I will start with Hesham. So he says, actually we talked about this, but how can we address the VNAs using the LLMs or like large language models or AI machine learning techniques? I think we discussed this, right?
LLM specifically. So we use all kinds of AI, explainable AI and machine learning techniques. And I showed you one sample such work, the one on joint admission control and slicing using multi-agent deep reinforcement learning. But we used all kinds of other techniques. For LLM specifically, because that's what the question is about, we have we have been looking at using LLMs, for example, because we are working in close partnership with Rogers and have access to operational data, so we are trying to leverage LLMs for example, incident management. So we have all the incident data and trouble tickets and mitigation workflows, and then basically what we're trying to leverage LLMs, for example, to assist, say, for example, network operators when they receive a trouble ticket, to suggest, like, for example, what the incident is about and what workflow they should follow in order to mitigate the problem. So that's basically an area where LLM can be definitely useful as providing assistance to network operators in addressing, among others, failures and their mitigation.
Thank you, Rauf. There is another question by David Abreu. Says he wants to know your opinion about the role of knowledge graphs for empowering network slicing decisions, particularly against fraud detection for telecom operators.
Yes. Yeah, no, so knowledge graphs is definitely a technique that allows you to basically to know how to navigate the system and understand what's going on. Yeah, I believe that I haven't really done work myself on knowledge graphs or leveraged knowledge graphs in this context, but my feeling is that there is actually a shift towards more LLMs and things like that, where like unstructured content and making sense of it out of tons of massive amounts of data using large language models and things like that. So I believe that there is actually in the community that's mostly focused on knowledge graphs, and obviously knowledge graphs can be used as a tool for network operators in different contexts. But there seems to be kind of move towards less structured data such as knowledge graphs to like unstructured data and knowledge using techniques such as LLMs. I'm not sure if I answered correctly your question, but yeah, I think that's at least from 30 miles.
Thank you, Rauf. So there is another question by German Svistunov. This is a too large, open question, long to answer, but will the integration of terrestrial and non-terrestrial networks bring new challenges to network virtualization? I mean, you already mentioned about the end-to-end issues. So, but please, whatever you want to say, it's fine.
Yeah, no, so that's definitely something that is happening. Say, for example, the integration of satellite networks with 5G, whether onboarding G-Node Bs in the satellites or using satellites as a backhaul or any combination thereof. There is a lot of work ongoing in that space. Whether this actually gonna bring or facilitate more virtualization, I'm not necessarily sure. Definitely here you will have to add into the equation in addressing end-to-end network virtualization. You have to add into the equation the satellite links and the satellite nodes, and I think that adds actually some level of complexity. I should say. If you are thinking low orbit satellites, that creates maybe increases path diversity, which is a good feature. We've seen, for example, in the work we've done for survival virtual network embedding, this is a kind of an assumption that we make, path diversity, in order to be able to do a reasonable number of path splitting and multi-path routing. So definitely, yeah. So the integration of satellite networks with terrestrial networks will add capacity, will add path diversity, will add nice features and options for carrying the traffic and slicing. Whoever or virtual network virtualization will have to add this into the equation, which is not already the very simple, but certainly an added complexity.
Let me also add to your answer for the person who asked this question. We did also research on this topic, especially for the CubeSats. We have a couple of papers on Internet of Space things, and we use these SDN and FV. So we have these controllers on the ground segments, which can handle the terrestrial network, also the CubeSats as well as the LEOs. And so we also did all the slicing, etc. We have patent and plus the papers. So already solutions are existing for that. Even we did also for underwater networks where the buoys are doing the slicing and the underwater devices are sending everything to the buoys, and the buoys doing slicing for the terrestrial network. So these areas are very active. So please go to the literature and find many papers already existing. So there is one more paper. There is more question. Tiago Cruz is asking regarding network virtualization. Many take SDN support for granted, with OpenFlow on its way out. Do you think P4? Yeah, P4 is right. Will be up to the challenge. Actually, that's what many people are using. All right. Are there any suitable alternatives? So P4 is but please go ahead. So.
Yeah, no, I think these are, I would say, two different things. I think SDN and SDN is more for network programmability, flexibility of how you handle flows in the network by software, as opposed to traditional networks that did that in some using hardware. But and P4 is more for the programmability of the data plane. So I would say these are two different virtualization. Let me put SDN and network function virtualization and P4 data plane programmability under the umbrella, let's say, of network softwareization. And I think it's a different concept from network virtualization. They can work together. You can imagine that you have a software-defined network and it's virtualized. For example, an easy way, an intuitive way to do that is to divide the flow space or partition the flow space. Remember, as I mentioned earlier, network virtualization is about partitioning the resources and allocating these resources to different logical or virtual networks, right? So in the context of a software-defined network, one resource that you can partition, for example, is the flow space, like the flow tables, and then allocate these portions of flow tables to different virtual networks that ride on top of that software-defined network, right? Yeah. Now, the other way around, you can think of slices or virtual networks that are software-defined, and you can have one, controller, SDN controller for each of the virtual network, and each virtual network will have a different controller that basically enforces different policies for that virtual network, like to support specific applications or whatever the reason that or why that virtual network was created in the first place. So I would say that just to summarize, network softwareization, SDN, P4, etc., is more there for network programmability, and virtualization is more for partitioning resources and allowing the coexistence of different application or services, whether they are software defined or not, on the same physical substrate.
Thank you, Raouf, and thanks to the audience for asking these questions. And I think we are done with the Q&A session. So I thank you again, Raouf, for this excellent webinar plus the Q&A session. So I let my dear colleague, Alessia, to ask you some life lesson questions. So again, thank you, and I'll be back soon.
Yeah, thank you, Ian.
Thank you so much, Ian. And thank you, Professor Butava. So we'll move now to the Wisdom Corner. I will make it short, don't worry. We would like to add a personal touch to this series of webinars. So that's why we have created this Wisdom Corner. I would ask my first question, if you agree. So which is your hard-earned life lessons or failure that you would like to share with us that might perhaps be helpful for somebody attending the webinar?
Wow, it's a yeah.
It's a non-common question, I know.
Yeah, I just didn't think about that. So maybe just to relate to the theme of my webinar, maybe this could be valuable to academics who are doing research in some areas, and we as academics, and we are subjected, and I think the industry to some extent, they are subjected to this technology of rapid pace, and to which technology is evolving, and very often forcing some people at least to move from one research topic to the next, just following the money or following whatever is hot for publications. I think the reason I say I'm relating to what the theme of my presentation, as I started working on network virtualization in the 90s, and I didn't give up. And sometimes it was cold technology, let's say, or a cold topic, and they continued. And you see that even though technology evolves quite a bit, I think there is renewed interest and new dimensions that get revealed when new technology arises, that basically put back the actual problem or back on in the scene. So I think perseverance, persevere in what you're doing, and focus on fundamental problems and try to solve them fully. Otherwise, it's just hopping from one topic to the next. I think you just you barely have time to scratch the surface, and that's an issue that can happen. So yeah, choose a topic that you like, that you are good at it, and at least that worked for me, and then try to address it, or address it fully. I think that's something that I believe worked for me, and so I don't pay attention to some of the noise, and we can afford that being in academia. I think it is less easy or less obvious in the industry, because it's a different context. But in academia, we can afford to to work on problems for a long time.
Yeah, thanks. And if you had to give an advice to students in which fields today, which topics would you recommend them to study? Is there any current trends or emerging areas of research that you find particularly exciting or promising, if you had to give an advice?
Yeah, I don't think anybody will listen to you unless you say you work on AI, right? So,
Oh, all right, I see.
regardless of what you say, everybody wants to do AI. It is an exciting field right now, for sure, with all the developments going at the crazy allure. I would advise them to follow Jan Kildes. He has always opened in the hottest topics, and but then to give a couple of concrete examples. I think networking is becoming a commodity, and I think what's happening in the wireless side has allowed networking to become to remain relevant in several last years. So there is a lot of things going on in that space when it comes to networking. I think something that was mentioned is definitely network automation, network intelligence, embedded intelligence is definitely something where one can leverage the advances in machine learning, in AI, for network operation, management, or even for designing next generation networks, is an area that are, in terms of technologies, there is more and more interest in quantum networks. I think, though we don't have quantum computers yet, but I think the promise of seeing quantum computers not long ago from now, or maybe next 10 years or so, they basically that's the question, what's after that? Once we have computers, then we need to interconnect them, and that's where networking will need to be reinvented, because the context is quite different. So I think these are two examples. There are more pressing issues, such as security. I think networks have done a great job bringing the entire world together, but then they are vulnerable. Not everybody is. They can be also weaponized for various things, including actually wars. And today's geopolitics have give us many examples where this is the case. So I think security and privacy and things like that are I think pressing societal needs, because we rely more and more on networks. These are a few examples that come to mind.
No, very clear, actually, very useful. Thank you. And if I can ask, what initially sparked your interest in your field of study, and how did you pursue it, like at the beginning of your career?
Sometimes things happen, right? When I was looking for a PhD, I was looking for an opportunity, and in particular, a paid one.
Of course, yeah.
So there was a good project. I take the opportunity to thank my supervisor of the time, Guy Pujol, many of you know. I had this project, part of the at the time, there was a program in the EU called Esprit, and so he was looking for a PhD student, and the topics spoke to me. Actually, I wanted to work in systems and networks, and that's what I did. And so I was more coming from the system side, and networks is close enough, and that project was more on in the area of network management. That's how I ended up doing my PhD thesis in the area of network management. And I chose to work on automation because I felt that was really important, and it continues to be important until this day. So yes, that's how it happened.
Okay, very, very clear. My last question. If you could tell us one of the most tangible contributions that you have made in your career that had a direct impact on your life, even personal or professional, that you're most proud of?
I think I think in his long introduction,
yes, true. Ian mentioned something. Yeah.
One can imagine that I had a long career already. So
very long, yeah.
let me say one instance that really touched me personally, more than anything else. Usually, we're happy to get an award or a chair or whatever, or a table or whatever. But then one that recently touched me quite a bit is nothing international. It's actually a local here at the University of Waterloo. That happened actually in 2024. I received the award for excellence in supervision.
Wow.
This award is actually, it came at a surprise because the nomination comes from students. Students
All
together
right.
and you need, I don't know, more than 10 or so former or current students that get together, write a nomination, write letters of support, submit that to the university. It's very, very competitive award. And then one day I was sitting there and I was told that I received that award. This touched me really, really quite a bit because, you know, it comes from what I think is maybe my most significant contribution, the training of these great kids that are now not so no kids anymore, and they are like, you know, professors and have leadership positions in the industry and very successful in their lives. And for many of them, they spend quite a bit of time with me, you know, a few years doing PhD, and they become like more than just students. So for me, that was like maybe, what touched me most, and that happened very recently.
Wonderful. I'm sure. Yeah, you're very proud of that. Thank you so much. We conclude here our Wisdom Corner and our webinar. So we thank you again for being so generous at the Wisdom Corner for sharing with us and for your very interesting talk. So Ian, we close this webinar.
I also thank Raouf, especially his last statement about the students. It's indeed, I have the same feeling.
Yeah.
They become your family members, you know, your own children, and it's very important that they recognize the role of the advisor, who is like, you know, in German they always call them Dr. Vater, Dr. Vater, the Dr. Father, and it's really important that the professors and students should create a very good relationship, like a family which will last forever. And it looks like Ralph achieved that. In fact, I mentioned that in my presentation of him, that he graduated many students who are successful in their careers. So thanks to Ralph, of course. Plus, his advisor is also a friend of mine, Guy Pujol. He was also one of those legends in France. He has the same achievement like Raouf. So it comes from this family, you know. So again, thank you, Raouf, and I hope to see you soon, latest in October, I guess, or maybe earlier. So again, regards to the family, stay safe and healthy. It was very good. Thank you.
Thank you so much.
Yeah.
And so Ian, we'll see you next week for our last
announce
webinar.
that, yes, Alessia, we should announce that this season will end next week. We have another excellent speaker, Enrico Natalizio. He is one of the big people at Technology Innovation Institute. He will talk about his basic and practical research on drones, and I'm sure that people will enjoy that too. So, and then the season will be over. So thank you again.
It will be our 10th webinar. So we had 10 webinars already in the first season. So thank you so much, everybody. Bye-bye.
Thank you very much. Bye. Ciao. Ciao. Bye. Ciao.